We can use the equilibrium constant expression for a reaction and data about the concentration of reactants and products for a system at equilibrium to calculate the value of the equilibrium constant. For these examples, we'll be using the decomposition of ammonia to form nitrogen and hydrogen gas. Okay, so if this reaction is allowed to come to equilibrium in the presence of a ruthenium catalyst, calculate the equilibrium constant for the reaction if the final concentration of ammonia, nitrogen, and hydrogen are 0.408 millimolar, 41 millimolar, and 41 millimolar respectively. So first of all, the ruthenium catalyst. A catalyst will speed up a chemical reaction, but it will not shift the equilibrium towards reactants or products. So that is information about how it has come and reached the equilibrium state. We're going to assume it's at equilibrium. That 0.408 millimolar is the concentration of ammonia. Now, anytime we're using equilibrium constant expressions, it's important that we input our data in units of molarity. Millimolar won't work, and so we need to write this as 4.08 times 10 to the negative 4 molar. These are the concentrations of nitrogen and hydrogen, and they're in units of millimolar as well. We need to change those to units of molarity, so this is 0.041 molar and 0.041 molar. So make sure all your units are in units of molarity if you're calculating equilibrium constants using concentrations. The second thing that you'll need is you'll need that equilibrium constant expression, and remember K is the concentration of products over reactants. So the nitrogen has no coefficient, so no exponent. The hydrogen has a coefficient of 3, so it's raised to the third power. And the ammonia goes on the bottom, and it has a coefficient of 2, so it's raised to the second power. Remember, you omit solids and pure liquids. That isn't the case with any of these. And if you've watched the video on writing equilibrium constant expressions, this isn't the same as the other ammonia example we used. This reaction's written the other direction. If we had it as a synthesis reaction, this would be upside down from where it is now. So be careful that you're looking at the reaction that your problem describes. So now we can just sort of plug those numbers in. And we have 0.041 molar for nitrogen. We're not going to include the units. 0.041 for the hydrogen, but we need to raise that to the third power. And 4.08 times 10 to the negative 4 for the molarity of the ammonia. And when we pump all these numbers into the equation, it comes out as 16.975 and should have two significant figures from those 41 millimolar numbers. So the equilibrium constant at whatever temperature this reaction came to equilibrium at will be 17. Now it's important to note this is specific to this reaction and the temperature. Equilibrium constants will vary as you change temperature. They can also shift as you change pressure. Okay, so to sort of expand on what we just talked about, we just calculated this as having a value of 17, and I'm going to go ahead and label this a capital K. When a system is at equilibrium, that equilibrium constant expression will be the same, and each of these first three are systems at equilibrium. I want you to notice that the concentrations are different, their relative ratios are different, but in each case, that value for that equilibrium constant expression will come out as 17. In contrast, this last set of data, if you plug all the numbers in, will come out as 2460. So I suppose that should be 2500 with two significant figures. And that's not the same number. This system is not at equilibrium. It could be at equilibrium at a different temperature. In this example, it's not at equilibrium. I can still plug numbers into that calculation, but if the system has not come to equilibrium there, that value may not be that 17 number. In this case, I'm going to label this as Q. It's called a reaction quotient. It's the same equation we just did. It's the products over the reactants. So it would be the concentration of the nitrogen times the concentration of the hydrogen cubed, concentration of ammonia squared. But it's not necessarily at equilibrium. When Q is equal to K, the system is at equilibrium. In this example, we have a Q, a reaction quotient, that's greater than the equilibrium constant. And if this is the case, these numbers are too high. Okay? Or you can look at it that the reactant's too low. In either case, the way for this system to reach equilibrium is to shift and convert some of these products back towards reactants. When the Q is greater than the K, the reaction or the system will shift towards reactants. But if saying it another way, the spontaneous direction for this reaction will be products converting into reactants. Conversely, if the reaction quotient is less than the equilibrium constant, then the way it can get to that equilibrium constant value is for the system to shift towards the products. And so this is one of the reasons you might calculate this value, is to check if a system's at equilibrium, or to predict, if it's not at equilibrium, which direction the reaction will proceed spontaneously.